So I would like to talk about identifying the dependencies in our complex systems and how they become the paths through which failure propagates, and what we can do to mitigate that propagation so failure doesn't travel too far within our systems. A little bit about me. I'm a distributed data systems engineer at a company called Wallaroo Labs, where I work on a system called Wallaroo, which is a framework for building scalable and distributed data processing applications in real time. And one of the biggest things that we emphasize is resilience, operability, and predictable behavior under heavy loads, and especially in the edge cases. And I've been at the intersection of infrastructure, data engineering, data science, and especially at the large scale and the real-time systems for the better part of a decade now. And there's one thing that I've learned is there is a pattern that pops up. I like to call it the USB pattern. You use it, you scale it, and then it breaks. Congratulations, now you're a DevOps. So I'd like to start, before we get into that, just a show of hands, who here is on call or has been on call recently? So that's about 3/4 of the room. Now, how many of you have designed the systems that you're on call for? About half of you who are on call. Well, you might be inclined to think that the pain that you're feeling, the pages in the middle of the night, are self-inflicted. And I want you to really rid yourself of that notion. It's not your fault. The failure that we have is inherent in these systems. It's inherent in the complexities and the dependencies and all the hidden coupling that we have. The failure is inevitable. It's just a normal part of systems. And because it's going to happen, it's just going to happen, and there's nothing we could do about it, maybe we should approach it in a more constructive way. So we can understand it, so we can understand what comes next, how to deal with it, how to cope with it. This will help us design our systems in a way that they can still perform their functionality and serve their purpose when they're experiencing internal disruption or partial failures under the hood. So let's look at how we can do that. We can use tools like dependency mapping, which help us understand how components are related to one another, how they affect one another, how they rely on one another. And that understanding informs our mitigation strategies, like isolation, redundancy, and graceful degradation. And once we do that, once we apply the mitigations, we're not done. It's not over yet. We've dealt with all the identifiable things, the known unknowns. And now we can start looking at the unknown ones, the unexpected failures, the edge cases we haven't seen yet. We could use tools like destructive testing in order to explore the space of failures we haven't met yet. And once we've understood our systems, we could apply end-to-end testing to verify those properties and behaviors and make sure that they still maintain them. And finally, when we realize that even then the search space is just too big, too large, and we can't explore it by hand or manually, or even with some automation, we turn to fuzzing, where we generate the test cases themselves, and we let the programs do the work for us. Because let's face it, our systems are pretty complex already, and it's only getting more and more complicated with every year that goes by. So I really can't stress this enough. The core concept of this talk is understanding. It's understanding the failure itself, how it affects our components in the system, how it affects the systems themselves as an emergent behavior of failure in components, and especially how it affects us, the humans in the equations, the operators, the users, the developers, everyone. So let's start right with the understanding. We want to understand how components relate to one another, how they depend on each other. And it's easier to show this with an example. So let's take Foobr. It's a fictional e-commerce platform. Foobr provides e-stores with inventory systems, a content management system, and payment processing. And then, of course, there's the little details, the database, the stores themselves, the vendors who give you all the revenue, the small things, right? Don't usually have to worry about those. What we want to do is draw the direct dependencies. I like to start pretty high, draw a box for a service, a box for the database, and add arrows every time there's an interaction between two different components. I can zoom in as I need to when the need arises, but staying pretty high level is actually quite useful at the beginning. The next thing we want to deal with is the indirect dependencies. These are components that rely on one another through an intermediate component. These are harder to see, and they could be deeper. They could be really deep in complicated stacks. There are tools to infer that, but at the end of the day, sometimes just grabbing some pens and some paper and drawing your systems again and again until you get it right is going to work pretty well for you. The next step is that we can identify the regions of isolations. These are parts of the system that don't really interact with one another. So maybe we can think about separating them from each other. These are great candidates for isolation. So let's remove this coupling and separate them into independent processes. Now, the map may have given us the hints, but at the end of the day, you need to trust yourself. You're the expert in your system. So maybe you should talk to your users, talk to your stakeholders. But at the end of the day, trust yourself that you will make the right call about what to separate, what to keep together, what relies on each other. And this might look a lot like breaking a monolith into service-oriented architectures or microservices, and that's because it is. I mean, the core idea is isolation. That's the whole point. We want to decouple as much as we can. And now that we have isolation, the time is really good for adding some hedges, or also known as not having all of your eggs in one basket. What we want to do is make our services redundant, especially the critical ones. So for Foobr, we want to add redundancies with the inventory system so that A-stores can have high availability. We want to add redundancies with the payments because, hey, that's where our money comes from. Duh. And of course, we want redundancies with the database. That's always the truth. Usually important. And again, this might sound pretty basic, and that's kind of the point. This is not rocket science. Oh, thank you. That is a good point. Should have turned that off. DevOps. Thank you, Vince. It's about understanding. It's about setting the plumbing. So again, just grab some pencils and papers, draw out your things until you understand them yourself. There's nothing special about it. It's just about developing the intuition and accumulating that knowledge. And you will find that over time, your understanding of it improves, and your choices of mitigations, your intuition about what to do gets better and better as well with the experience. Somewhere between isolation and redundancy, there's this concept of graceful degradation. This means that with only some availability, we can still provide value. Maybe it's not the entire value of the system, but the users can still use it. In Foobr, the content management system serves an entirely separate set of users than the inventory and the e-stores. So if we took that down, maybe for service like we used to do a decade ago, and maybe it just went down on its own, that should never affect the stores themselves. It shouldn't affect payment processing. Shoppers can still purchase goods. But even then, after we've done that, we've added the graceful degradation and the isolation and the redundancies. Failure is still going to happen because failure is inevitable. There will always be a hidden dependency in the system, something that we didn't know about, something that maybe only failure revealed to us. And then we could turn to tools like destructive testing. Those help us understand how things behave when failure does happen. The great benefit of destructive testing is that when we introduce the failure, we treat it as a teacher. We embrace it. We add fault injection, where we introduce those failures and eliminate components that that the system originally relies on. We interpolate the dependencies. that we didn't know about before. And we can extrapolate some properties about the system itself, such as that, hey, your database is a critical dependency, and without it, nothing works. But in the end, destructive testing is just an idea. It's the idea that failure is a teacher. It's there to teach us what we should do next. And unfortunately, we can't always use it in production to learn. Maybe the stakes are too high. Maybe you just don't have the buy-in, or maybe it's too expensive. But if we still want to learn with it, we need a way to do this outside of production, a way to play around with failure, see what happens to our systems. There, end-to-end testing has an answer for us. It's a methodology of testing an entire system in the same way that it will be used in the real world, in production, with all of the components and all of the services live and functioning. The entire system is tested as a black box with simulated load and real-world condition, or as close as we can make it. And we do both the happy paths in those tests and some sad ones. Those are the ones we want to learn from. These allow us to observe, to measure, and to monitor that the properties that we care about are being maintained in the system. It's kind of like taking all of your integration tests all at once and just running them for the whole system. It's often a lot simpler to reproduce the real-world conditions or similar conditions to the real world in an end-to-end test than it is in an integration or a unit test. And I think that's one of the biggest benefits there. But the end-to-end testing itself, it doesn't come for free. It takes quite a bit of instrumentation to get it going, especially if your systems are large and have a lot of dependencies. Anybody here has to instrument large multi-cloud systems for tests or live? One. How many of you have, if you wanted to do this, would have to set up a database, set up a web server, set up your logging, your monitoring? How many systems on average do you have to turn on in order to do this test? 5? 6? Raise your hands. 3? When we test ours, we need about 10 systems to be set up, usually distributed, usually across more than one cloud. The cost of just building the code, building the tools to do that is not negligible. So end-to-end testing is usually something you do further down the line, just because of how expensive it is upfront. There's usually a distributed component by the time you do this. Sorry?
You're not using your existing monitoring systems to do that end-to-end testing?
And what? I'm sorry?
You're not using your existing monitoring systems to do that end-to-end testing?
We do both the monitoring systems in production, and we run a separate monitoring system as part of the end-to-end test. It's a part of that entire unit. So monitoring a separate instance of it is a part of the end-to-end test. It's not the same one.
Okay. I thought you meant you had to spin up 10 additional things that you don't normally run.
Yeah. So it's not like an integration test where we just run the core service with the thing that it talks to on its own. Back to the requirements. With end-to-end testing, to have the instrumentation, the distribution. If you have a distributed system, you have to figure out how to control remote machines, how to talk to them, how to measure on them. And measurement itself is actually really hard. Sometimes it's easy, you could just query a service, it's alive, yay, you got a ping back. Other times you're trying to look at something that may not even be visible. It might be an opaque state of a system. It might be the condition of a database, it might be a single record in a table, or it might be some internal in-memory state that is just not visible outside of a debugger. But this is what you're testing, so you have to put in the work and figure out how to do this for your specific system. Even then, even after we added end-to-end tests and the failure injection, and we did all of the mapping and all of the isolation and the mitigations, failure is still going to happen. You're never going to escape this fact. It's a big universe, and it's just full of failure. Not us, I mean our systems. That's important. So we can't possibly hope to explore it all on our own. Unfortunately, there's this really cute idea, not cute, really smart idea from functional programming called property-based testing. It's the idea that instead of specifying the correct result for a function like you do in a unit test, like an oracle, we specify the properties that should be apparent during the run of the execution of a function. This should be true for all inputs, forever and ever and ever. These are all unicorns, by the way, obviously. But for a more precise definition, unit testing is usually the kind of testing that consists of two components. The first is a fuzzer. And a fuzzer is a thing that produces input for the test. That's all it does. It generates test inputs. The second part that you need is a library of tools for making it easy to actually construct and execute those tests. As it turns out, we just spent a lot of work building end-to-end testing systems. So we have the second part mostly ready. You could usually repurpose an end-to-end system for this stuff. So mostly, it's just a fuzzer that we're missing. I told you the dog will be back. The fuzzer produces data for the test. It might come from a large corpus. It's usually or possibly dynamically generated. And it might depend on the previous results of the executions that we've just run. But in order to see whether the test passes or fail, for the system testing, the fuzzers usually need to be system-specific. For Wallaroo, we have to generate a different sequence of events than you would have to use for Foobr, for the eStore, for example. So let's look at a simple example of property-based testing. What we have here is a function that does a sum on two numbers. It literally adds them. This is in Python. And here's what the unit test looks like. This is called an oracle test. We've given it an input, and we've just given it the result. If it doesn't match, it's a fail. OK, it's pretty good. Now, what happens if our sum function wasn't behaving normally? In this case, we injected a bad behavior. But would our unit test find this? It wouldn't, right? So maybe let's write a property test. And here I'm doing this by hand just to show what it is. I'm sorry? Again. Computers. So here we're doing this by hand. We're pretty much just running a million iterations where we choose a couple of integers between -1 billion and 1 billion. And then we compare the result of our sum function to the result of the native addition of two numbers. This massively increases our test coverage. And it trivially also finds that error in our property. So this is a really basic concept of property-based testing. This is the easy part, right? Test a single function, no side effects. It seems kind of easy. So let's do this for a system. Let's do it for Foobr. For Foobr, we need to generate the input data. For shoppers, they're trying to buy things on the store, maybe look at the prices, maybe wait for a sale. And for the vendors, who are either updating through the content management system or trying to get their money back from us. They probably want it. But then we get to the more interesting parts of our fuzzing for a system, which are the system events. These are the events that the system experiences. This is where we depart from the normal version of property-based testing, or what we would expect in functional programs. For system events, for the end-to-end test, what we care about are things like network faults and recovery of the network. Maybe service faults and recovery there. Sorry. And those are the cases where fuzzing a system test become quite interesting. So here I'm going to switch to fuzzing Wallaroo. Wallaroo is a framework for building real-time distributed data processing applications. It is clustered, it has internal workers, and it runs user-defined application topologies. In order to test it, we need to send it some input data. In this case, we send partition data based on a key value that is just an ever-increasing sequence of numbers per partition. And we also need a way to validate that nothing has broken there. So we use, for each key, we just make sure that the sequence that comes out of it at the end has no loss, no duplication, and no reordering. These are the basic consistency guarantees of Wallaroo. And then we add, once we have that test, the basic signal that tells us whether the test has failed, we add the system events that we really care about testing for. We add the cases of adding nodes and removing nodes, where we shrink or grow the cluster. And then we crash some nodes and recover those as well. And sometimes, if we feel really, really brave, we start messing around with the network. Lastly, the third dimension with Wallaroo specifically is the applications themselves. Because Wallaroo is a framework for building applications. It can describe a lot of different types of topologies. So we couldn't run a single test. What we ended up doing is writing a tool that produces applications based on canonical topologies, or topologies that would have the same type of connections underneath the hood that a normal application would have. And so we compose them out of sources and sinks and computations with and without state, partitions, and filters and multipliers that change the output cardinality of any computation. Sorry. And in the end, this produces a large suite of tests that allow us to test multiple types of applications under multiple conditions with multiple types of failures that we didn't have to invent ourselves, or we didn't have to wait for our users to discover those in production. And when you turn that on, the first time I turned it on, it was an alarmingly large number of bugs that were found. I think we ran about 100 tests, and we found probably close to a couple hundred edge case bugs. Some of them were just off by one errors, other ones were problems with the original algorithm. And the great part about it is that none of those bugs ever made it out to a production system, to a user, because we found those early without having to wait for the users to discover those for us in their production. So to summarize, the key approaches to applying resilience engineering all start with understanding, with mapping how things relate, how failure is going to propagate through our system. From there, we move on to the mitigation, where we add isolation, redundancy, and graceful degradation. After we've done all of that and dealt with the easily identifiable parts of the system, we start tackling learning and understanding, learning about new failures, things we couldn't predict ourselves by destructive testing. And finally, we automate the monitoring and verification of those properties that we've identified with end-to-end testing and system fuzzing to look for more. So these are the key approaches that I use personally for building resilient systems and designing systems that work well. And I found that those are usually the most helpful ideas to apply for your own systems. None of this was about the tools or the programs or high-level academic stuff. It was just the things that you can think about yourself. Mostly things that you could do with pen and paper. And I think this is a really powerful idea. But first, the failure is a truth of life. It's going to happen. There's no system that is immune to it. It's not our fault. And understanding it is what helps us live with it and cope with it and identify the correct next steps after it happens. Because resilience, at the end of the day, is just a property of being able to sustain internal failure without leaking it externally to the users of our systems, without losing any quality of service. So that's all I had for today. Are there any questions? Yeah.
For end-to-end testing, we use fuzzing to generate the data, to copy data from production to the end-to-end test.
Okay, I'll just repeat the question. The question was for end-to-end testing, whether we use fuzzing to generate the input data, or we just use that sequence of data.
Yeah, or you just mirror data from production and use it in your internal testing.
Yeah, so for Wallaroo specifically, we generate data because we're not testing a single production application. We are testing a range of possible applications that users might build. And so what we actually do is we built a special apps that are basically tracers. And we send data through that shows us, as it goes through the app, how the state has changed internally. So what comes out at the output of the application is the sequence of transitions of state. For that, we send a special signal in, which is just incrementing numbers with a key. And what we get outside at the end is key and numbers as well. That's just a signal. So that's not the part that we fuzz. That's the thing that we test out, how we use to measure the property of the consistency of the internal state. What we fuzz are the system events, the addition and removal of nodes, and crashing and recovering different components.
Have you looked at using tools like Zipkin to generate the inter-service dependencies?
Yes, I have. There are tools for sniffing your network to identify how things are connected. The name escapes me right now, actually. There's an interesting blog about just writing it by hand, this service depends on this service, into a Neo4j table and letting it draw a graph for you to show you the actual diagram. Mostly, I like to do it by hand because if I can't draw it by hand, I think the service is usually too complicated, at least for me, to make heads or tails of. I think it's off.
Testing. You can sometimes use like NetFlow or SFlow data for that, but it's not. You're going to miss a bunch of the details that you wouldn't get from a sampling system otherwise. Yeah.
Personally, I think the greatest teacher of what depends on what is the failure. I like to think of it as a large Hadron Collider. You're just throwing things at each other, throw a lot of traffic at it, throw some failure at the same time, and watch what fails and what failed right after. Those were probably dependent on each other. Otherwise, they wouldn't have failed together.
Have you looked into things like varnish replay and things like that, where you can basically save real data from production and then replay it back to another testing system that is a copy of production, or even production if you wanted to? I have been looking into that for API testing and stuff like that, but I don't know if it's easy, because then you had to, like, the response back, you had to modify it before and so on.
For us, we actually have a special flag. So this is system specific, this sort of stuff. So I can't answer for a general use case. I can say that for Wallaroo, it has a resilience built in, which means there's some side logging happening that just generates a log of changes. We have a special flag that can enable this for the input sources. And so we could replay from the source everything that has happened. And that allows us to test a real world use case if that was on, if resilience was on for the user. If they're running without it, then, that's the same problem as any other system. You have to capture your traffic somewhere.
Yeah. Thank you.
Yes, this is Maru, my dog. Here, let me. Oh, by the way, the talk slides are available on this website, which is just mylastname.ca. The slides are available there if you would like them. If you want more photos of the dog, let me just. There you go. This is Maru. He's a cloud, which I guess is appropriate. He's taught me a lot of things about clouds.
Just one additional comment. It's not so much a question, but a comment. So I'm hearing talk about people suggesting copying production data into the test environments for end-to-end testing. Mm-hmm. I manage a team that actually sets up test environments, and I wouldn't suggest doing that unless you've suitably analyzed your data to see if there's any privacy concerns, because once you start porting that data into a test environment where developers and testers can take a look at personally identifiable information, it's dangerous.
So I'd like a quick question. Who here has to deal with compliance, either medical or financial or other legal compliance? Okay. Yes. Don't copy production data. It's going to break compliance and put you on the hook for a lot of things. Even if you think you've anonymized it, you probably didn't. The best approach I have found is measuring histograms of shapes of the data. What you care about is the shape, not the content. Maybe that means there are different types of traffic. Like in Foobr's case, it was shoppers and vendors. And you really just care about having 10% vendor traffic and 90% shopper traffic, of which 10% of that is actual purchases and transactions. That's the shape of the traffic. That's what you want to test. But then once you're dealing with testing the shape of the traffic, you might as well test the edge cases and make it really extreme, because that will inform you of what happens to the system under those extreme cases. It will tell you about the limits. Okay, thank you.